The images are shocking.
The past 3 summers, portions of Lake Erie were covered with a green slime, blue-green algae.
This is straight from Lake Erie. This extends 50 miles. I don't know how close you can see, but you don't want any part of it.
What are harmful algal blooms, and why do they happen? Chris Winslow from Ohio Sea Grant and Amy Brennan from the Nature Conservancy explain.
Harmful algal bloom is an organism growing in excess. And in this case, algae is a pretty generic term. What this actually is what's called a cyanobacteria. So it is a bacteria. It's a bacteria that has the capability of producing toxins under the right conditions. They are not marine organisms, so they are found in freshwater systems.
The western basin of Lake Erie is shallow. It's warm, and there's a lot of drainage coming into it that has a lot of nitrogen and phosphorus, which is the same thing that people put on their lawns to be able to grow their grass. So this is basically growing the harmful algal blooms in the western Lake Erie basin. It's just the perfect storm of criteria between it being warm enough, sunny enough, and having the right nutrient load to be able to drive those blooms.
In 2012, the United States and Canada signed the Great Lakes Water Quality Agreement with a goal to reduce the amount of phosphorus entering Lake Erie by 40%. While great strides have been made, the severity of harmful algal blooms in Lake Erie has increased over the last decade. Between 2008 and 2018, 7 out of 10 years have had a significant or severe bloom.
Phosphorus is always described in one fraction, and that's total phosphorus. And so forever, anybody who went to an educational seminar or went to college or a university or wherever, and phosphorus was talked about, it was talked about as a total P that was essentially immobile. And once it's in the soil, it binds the soil and it stays there. Well, what we've been finding through research and just through increased knowledge is there's a fraction that is dissolved, and it actually comes off, and it comes off with moisture. And that fraction is making its way into the waterway and then causing issues all over the state and all over the country in terms of algal blooms and just really fouling up water here and there.
The majority of land around Lake Erie is used for agriculture. Since 85% of phosphorus comes from non-point sources in the watershed, researchers are focusing on ways to reduce phosphorus runoff from agricultural fields.
Point sources, things like your municipalities, your cities, maybe someone who has like a permit to discharge into a waterway, like a factory or a large business. And then there's non-point sources like, the landscape around you, farm fields, yards, things that you just really can't quantify into like a single pipe type of a source. And those are the areas that are the most concerning at the moment, especially in the western Lake Erie Basin.
The watershed that drains into Lake Erie is greater than 7 million acres, spanning parts of Ontario and Indiana, Michigan, Ohio. And so when you want to address this influx of nutrients into the system that drives these blooms or causes these blooms, it's difficult to get a lot of boots on the ground to figure out where it's coming from, where are kind of key concentrations of this runoff versus places that aren't contributing nutrients. And so what models allow you to do is look at characteristics across the landscape and make educated guesses.
A research team led by the Ohio State University College of Food, Agricultural, and Environmental Sciences recently finished a unique multi-modeling project to determine which management practices could have the biggest impact on reducing phosphorus runoff in the Lake Erie watershed.
The model that we used for all of the scenarios that we ran is the Soil and Water Assessment Tool, or SWOT model. And this model is used globally and is the most commonly used model to look at the effects of agricultural practices on water quality.
It wasn't just one model from Ohio State University, but it was a multi-modeling effort. So we had faculty and graduate students from Heidelberg University, University of Michigan, University of Toledo, and LimnoTech, as well as USGS that participated in the project.
The team used models called sensitivity analyses to understand how each best management practice would work on a large scale. What would happen if farmers adopted practices such as the use of cover crops, timed manure application, or controlled drainage across the entire watershed?
Best management practices is a really generic term for anything that we can do that's going to do a better job of managing those nutrients in the field or on the edge of the field or even downstream of the field before it gets down to our water resources.
The sensitivity analyses are at 100% adoption across farmland or eligible farmland in case of drain water management where you have drainage, but those are not feasible. You know, it's not likely that 100% of cropland will adopt a certain practice, and it's probably not the right thing for 100% of cropland to have the same set of practices because fields are different and producers are different.
Ultimately, no single scenario was able to meet the reduction targets, as signified by the red line. However, bundling best management practices proved more effective, leading to the biggest reduction in phosphorus runoff that leads to harmful algal blooms.
In those final bundled scenarios, we pulled together from the literature, from farm surveys, and from our stakeholder group's expertise, a list of practices and adoption rates for those practices that might be feasible in the near future in this watershed.
That was something I think really that moved things forward. Instead of having a very pie in the sky idea and an idea of a list of practices that really weren't going to be adopted at that level, this allowed us to look at a more realistic scenario.
Each of the scenarios, there's a bar and there's whiskers. The bar shows the mean of the models. This is the average of those 5 models. This is what we would expect, our best guess, given all the modeling that we're doing and all of the science that we've incorporated. And yet those whiskers, in some cases, show a large range. We could actually have more benefit from these practices or less benefit than what our average is from our models.
Well, I think one of the big lessons here is that the scale of the level of implementation we need to see of practices is incredibly high. It is much more than what we're currently seeing today. We need to have a very high level of adoption of not just one practice, but a suite of practices across the landscape.
One thing I want people to know about this project is that it's done for the farmer's benefit. So it's done to help reduce nutrients off their farm, which ultimately will either lessen the amount of money they spend on their farm or increase yield, which kind of does both. But it's done to not be in spite of production. So we want to make sure that food is produced, safely and as efficiently as possible, and we want to make sure that the farmer is able to continue on for generations and generations. But also, we want to make sure that we can keep reducing that fraction of nutrients that are coming off of the farm fields, and lessen that impact that we've seen downstream or in lakes or wherever.
The first thing that we learn is that there are many different pathways towards reaching targets. We don't have to select just these 3 practices or these 2 practices to try to approach our targets. We could select among a larger set of practices. A second message is that widespread adoption at greater than 50% of cropland touched by more than one practice is not enough to meet our dissolved reactive phosphorus target, may not be enough for our total phosphorus target of 9 years out of 10. And so that message is difficult. What do we do with that? We do see, though, that we're approaching those targets. So when we look at the flow-weighted mean concentration graphs, we see that in the case of total phosphorus, some of these combinations of practices pretty much get us there to that target. A final message that we see in those bundled practice results is that even with widespread adoption needed, it could be beneficial to target or prioritize practices in certain places.
Whatever we can do to get the fertilizer off the surface and get it into the ground, that's probably the most effective, best management plan out there. So if we can promote subsurface application of fertilizers, that'll go a long way to reducing the nutrient runoff leading to harmful algal blooms.
This is also not an issue that is just related to Lake Erie. There are harmful algal blooms that are happening in lakes and embayments across the world. And all of the lessons that we're learning here in Ohio are going to be shared throughout the state, throughout the country, and throughout the world. And I think that's a really interesting opportunity for us to get this right.